This video is brought to you by mywayteaching.com.
In this part, let us study potential energy in an external field. Okay. The source of electric field was specified, the charges and their locations and potential energy of the system of those charges is also determined in the previous cases, isn't it? Now, we are going to study potential energy of a single charge. First part, potential energy of a single charge. Okay. See here, what is the potential energy of a charge Q in a given field? So here, the main difference is that we are now concerned with the potential energy of a charge in an external field. The external field E is not produced by the given charge whose potential energy we wish to calculate, but this external field is produced by sources which are external to the given charge. That is the main difference here. The unspecified, what is specified is the electric field E or the electrostatic potential V due to external sources. So we assume that the charge Q does not significantly affect the sources producing the external field. This is possible only if Q is small or the external sources are held fixed by other unspecified forces. If Q is finite, its influence on the external sources at infinity produce a finite field E in the region of interest. So, we are not interested in the potential energy of the sources producing an external electric field. Now we are going to calculate potential energy of a single charge in an external field. So the external electric field E and the corresponding external potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to the point P, isn't it? Thus, work done in bringing a charge Q from infinity to the point P in an external field, we are going to consider it as Q into V. This work done is stored in the form of potential energy of Q. If the point P has position vector R relative to some origin, then we can write potential energy of Q at R in an external field is given by potential energy of Q at R in external field is given by Q into V of R, where V of R is the external potential at the point R. Okay. Thus, see, if an electron with the charge Q is equal to 1.6 into 10 raised to minus 9 coulomb is accelerated by a potential difference of 1 volt. It would gain energy of Q into delta V. That is again 1.6 into 10 raised to minus 19 joules. The units based on electron volt are most commonly used in case of atomic, nuclear and particle physics. Okay. This is about the potential energy of a single charge. Potential energy of a system of two charges in an external field. See, now we may ask, what is the potential energy of a system of two charges Q1 and Q2 which are located at R1 and R2 respectively in an external field? Again, first we calculate the work done in bringing the charge Q1 from infinity to R1, isn't it? So in that step, the work done is given by Q1 into V of R1, and next we consider the work done in bringing Q2 to R2. In this step, work is done not only against the external field E but also against the field due to Q1. So in that case, work done in bringing Q2 is given by Q2 into V of R2. Work done on Q2 against the field due to Q1. This is work done on Q2 against the external field. If you consider work done on Q2 due to field of Q1 is given by Q1 4 pi epsilon naught R12 into Q2. So, potential energy of the system, the total work done in assembling the configuration, that is given by Q1 V of R1 plus Q2 V of R2 plus Q1 Q2 by 4 pi epsilon naught R12, isn't it? So this is the total work done in assembling the configuration, that is potential energy of a system of two charges in an external field. Now let us see a simple problem. Determine the electrostatic potential energy of a system consisting of two charges 7 microcoulomb and minus 2 microcoulomb and with no external field, placed at minus 9 centimeter, 0,0 and 9 centimeter, 0,0 respectively. And the second part is how much work is required to separate the two charges infinitely away from each other. Okay. Let us find the solution. And before solution, there is another third part. The third part of the question is, suppose that the same system of charges is now placed in an external electric field E is equal to A by R square, where A is 9 into 10 raised to 5 coulomb per meter square. What would be the electrostatic energy of the configuration B? Okay, so now let us find the solution for the first part. Electrostatic potential energy of a system consisting of two charges. So we know the equation, U is equal to Q1 Q2 by 4 pi epsilon naught R. 1 by 4 pi epsilon naught is 9 into 10 raised to 9 Q is 7 microcoulomb minus 2 into 10 raised to minus 6 into 10 raised to minus 6 is 10 raised to minus 12 and 0.18 R. Okay. Which gives minus 0.7 joules. This is the first part. Now let us see the solution for this second part of the question. Second part of the question is, how much work is required to separate two charges infinitely away from each other? So W is equal to U2 minus U1 that is 0 minus U 0 minus 0.7. Just now we calculated that one. In the first case it will be 0. So that is equal to 0.7 joules. This is the work done required. So now let us go to the third part. Same system of charges is placed in an external field. What will be the case? We already know the equations. The mutual interaction energy of the two charges remains unchanged. In addition, there is the energy of interaction of the two charges with the external electric field. So, we find Q1 V of R1 plus Q2 V of R2, isn't it? So that is A into 7 microcoulomb 0.09 meters plus A into minus 2 microcoulomb 0.09 meters, and the net electrostatic energy is given by Q1 V1 of R plus Q2 V of R2 plus Q1 Q2 by 4 pi epsilon naught R1 2. So here A 7 microcoulomb 0.09, A minus 2 microcoulomb 0.09, and Q1 Q2 that we already calculated, that is minus 0.7 joules, isn't it? So here we know the value of A, which is already given in the equation. So if you calculate that, we get the net electrostatic energy. Isn't it? That is A is 9 into 10 raised to 5. which gives 70 minus 20 minus 0.7. So the net electrostatic energy is 49.3 joule. So this is the electrostatic energy of the configuration. Okay.